Hi everyone, and welcome back to NL 582, Modeling and Control of Electric Machines and Drives. Last lecture we started talking about modeling of DC machines, and we discussed what we mean by modeling, and we started talking about the equivalent circuit diagram of the armature. So before I jump into this, let me just have an important hint for you guys, and it helps a lot understanding how we built the equivalent circuit diagram of this machine. I'm saying this for you to know just every motor has internal generator, and every generator has an internal motor. What I mean by this, let's have a talk about this for a little bit, okay? So going back to talking about the theory of operation of the machines, and I'm gonna start talking about a motor. How we get a motor working, yeah? So in a motor, we apply external voltage, yeah, electric voltage to the terminal of the motor, yeah, on a coil, or talking about coils, whatever it is, just one coil or multiple coils. Typically it's multiple coils in the motors, cutting magnetic field coming from poles, yeah. You just apply voltage to some coil while these coils cut a magnetic field. These the conditions you need to have a motor, and now you have a torque produced and rotor starts rotating, yeah. For now, that's how we understand how the motor operates, yes? But looking at this condition, now the motor starts rotating. You have north and south pole, and you have a rotor inside that have more coil sides. For this, just one coil. We have two coil sides like this. The whole point is, once you have a torque production, that means this rotor will start rotating like this in whatever direction. Okay, by this means, while this starts rotating, okay, that means we have coil or coils rotating, cutting magnetic field. And this reminds us of the conditions we need to get a generator. To get a generator, you need a coil moving inside a magnetic field, okay, and that will give you just a certain amount of voltage will be induced on the coils, opposes the external applied voltage. That's what I mean by you have a small generator inside this motor, okay? Why? Because once the motor starts rotating, that means these coils are rotating, cutting a magnetic field, and this is the typical conditions you need to get an induced voltage generated inside the machine. Okay, guys? And this means, and that's why, if you remember, when we draw the equivalent circuit diagram of the DC machine, we have it like that. Right there, we have the applied voltage, V terminal, or applied. Okay, this is the applied voltage. Okay, and inside the machine, you have a certain amount of induced voltage, that is E armature. Okay, and this is induced voltage inside the coils because the coils are rotating inside a magnetic field, and here is the polarity of it. It will be like that. Why? because it has to oppose the voltages, the main voltage, because the main voltage is trying to pass a current in this direction inside the machine, IA, while this voltage will try to get the current getting out of the machine. Why it's this? Because basically it's Lenz's law, like we said in the last tutorial. According to Lenz's law, it is just any induced effects will have an effect that try to oppose the main source of it. Okay, guys? And that you'll find in any physical system, and it's the source of equilibrium, actually. Okay? If this doesn't happen, the system will not come to any stable point at all. You just apply voltage, and this voltage applies current, and you'll start getting higher and higher currents without a stable point. The whole point here is just you apply a terminal voltage, and certain amount of induced voltage is induced inside the machine, and the current will equal V terminal minus EA over RA. Okay? This EA started going up with the speed, because you know EA, to calculate it, is just K phi times omega m. So while the speed of the machine goes up, this induced voltage goes up. Okay? And this means the current starts going down until it just settles down to a certain point. Okay? And that's what's happened inside the machine. Okay? That is the armature equivalent circuits model. That is how we model the armature of the machine, guys. Okay? We are talking about a motor like here. We have V terminal higher than the induced EMF, like we said. Because this armature current equals V terminal minus EA. And while V terminal is higher than the induced EMF inside the machine, the current will be having this direction going from the source, the applied voltage, inside the machine to create the torque, and that's how it's considered a motor. Okay, guys? But what about the generators? Following the same sequence, we apply an external mechanical torque to rotate the rotor, which carries coils or winding, rather than saying inside, let us say cutting the magnetic field of the poles, yeah? And that's actually all the conditions we need to get a generated voltage, because that's a generator. So voltage is induced in the coils, and now you have generated voltage. That's a generator you want to have, yeah? But what will happen now? What happens is we apply this voltage to external electric load, resistive load R, L, or C, whatever it is. Okay, guys? Why? Because that's why we get a generator. We get a generator to feed electricity to a load, yeah? So we don't just have a generator and leave it open circuited like that, generating voltage, and we're not getting any use of it. The generator is connected to electric loads, like you connect it to any home appliances you have, or any industrial application you need to feed electricity to. Okay, guys? What happens when we apply a voltage to a load? It's Ohm's law. Okay, what will happen that certain amount of current will flow from the coils to the load, and that is what we need from a generator. Okay, but now you have that certain amount of current is moving inside the coils, so that means we have current moving in coils while cutting a magnetic field. Remember, that is the whole condition we need to get a motor. Okay, guys? So, torque will be developed by this current opposing the external torque. And that's what I mean by you have a small motor inside the generator. So you apply an external torque from outside. It's a mechanical torque coming from anything that's forcefully rotating the rotor of this machine. So these coils will cut the magnetic field coming from the pole, and induced voltage will be just generated, and that's what you need from a generator. But once you apply this voltage to an external load, current will be moving from the coils to the load. That means your coils of the machine will have current moving through them. And once you have coils carrying current inside a magnetic field, a torque will be just generated. It will be right to act like a motor. Okay? But this internal torque will be basically opposing the torque applied from external. So if you apply the external torque external or applied, it's trying to go that way, and that means the speed of the machine will be trying to go this way. The internal induced torque will be trying to go in the other direction, torque induced. That is the internal torque inside the machine. That is the internal. Acting like some sort of a brake, because it's trying to make the shaft or the rotation go in the opposite way. Yeah, it will not be able to do this because the applied torque or the external torque is higher than this induced torque, because we are talking about a generator here, not a motor. Okay, so the applied torque is higher than this induced torque, but this induced torque will be there whenever you have current still in the machine. Okay, and this acts as a sort of a brake, getting the speed of the machine actually to be stabilized. It's the same principle we dealt with when we talked about a motor before. It is the induced voltage, that's the thing that brings the current of the machine to a stable point, to equilibrium. It's the same idea here. If we don't have this induced torque inside the machine that acts like a brake, the speed of the machine will keep going up. It will not be stabilized. Okay? So you apply an external torque, and the machine creates its own induced torque, which opposes this external torque, but it's less than it. Okay? So by this equilibrium, you have a stable speed, and the machine will be just running smoothly at a certain speed. Okay, guys? So those are the hints I've been just trying to let you just have them in your mind, and that's how actually the machines are working. Okay, guys? Hope you understand this. I talked a little bit about this in the last tutorial, but I needed to have more emphasis on it starting this lecture. Okay, guys? Okay, so let's move on. So I'm gonna get you the photo of the whole machine we've been just talking about again. Okay, guys, so remember like we said before, it is just in any kind, or in this machine, practically the DC machine, okay, the rotor carries the armature winding, like we said before. The rotor winding is the part where the electrical part of the energy conversion process happens. That's why the rotor here in the DC machine is called the armature. Okay, guys? So the rotor carries this armature winding connected to the brushes, okay, and commutator, and that's why it's just being unipolar rather than to be just unidirectional, rather than to be bidirectional, if you remember when we're talking about. So that was the rotor inside here, so that this internal cylinder here is the rotor, and here's the rotor winding inside it, and you know this is the commutator springs, and this guy here the brushes, and you have another one down here. This is your brushes. Okay, so that is the rotor of the machine. Okay, what about the stator? The stator of a DC machine is the field winding, or just say it carries the field winding, sorry. So we call the stator the field member. Okay, that is the source of magnetic field. And where the source of magnetic field, here is these poles. It is an iron pieces like this. Okay, this piece and this piece, and you have it, we just completing it like a cylinder like this of iron or steel, again to increase the flux density, because the flux lines likes to move through these magnetic materials, the steel and iron, and we just wrap along it these coils like this. Let me make it in blue. So these coils here are the field winding, and this is the stator core. Okay, guys, so here is the field winding. What are you talking about here? So the stator carries the field winding, okay, or let me say, or the poles in general, because if you remember, we can create this magnetic field we need from winding or from prime magnet field. Okay, so the field can be coming from even permanent magnet poles. Okay, and this is usually we use in small machines, the ones you can find in the toys and all that stuff, or can be created by field winding coils like we say in here. Okay, and this is the typical use. Okay, so you just have coils carrying current. Okay, so let me just draw this in a 2D fashion just for you to be able to see it well. So the whole point, remember those pieces we have been talking about before, it is just you have magnetic poles will be just like this. Okay, guys, and you have the coils like this. So you just put a coil here, and you just take it to the other piece. Okay, guys, and now we have external terminals of this like this, and you can apply just voltage here, and this voltage will pass current, and the current will go through these coils and create you the magnetic field. Okay, but we don't leave it like this. We complete this to create a cylinder like this. Don't mind my bad circles, sorry, but you get the point. So these are iron or steel core. Why? Because it increases the flux density. And here is the field coils or field winding, because you have multiple coils here. So one of them will be north, the other one will be south. Okay, only by just making the direction of wrapping the winding from one of them to another are different. So one of them will be north and one will be south, just like this. Okay, I remember this from electromagnetic field studies. It is just the direction. If you have a piece of iron like this and you just have a coil wrapped by this direction, okay, and the current is going from this like this, I will be creating a magnetic field just going around like this. So from here, this will be the North Pole and this will be the South Pole. If you just reverse the direction of wrapping, so rather than the coils just going from the top like here, I will be just making it from down like this. Okay guys, so I just switched the direction of rotation, direction of wrapping these coils. Okay, so if the current go in the same direction, the direction of the magnetic flux will be just switched and you have a North Pole here and a South Pole here. Okay guys, and that's how we just from these coils here, we just create a North Pole and a South Pole just by switching the direction of wrapping these coils like this. Okay, so we have in our machines two sets of winding, the armature winding on the rotor and the field winding on the stator. Okay, and it depends how you can connect them. Okay, and that's a very important matter I'll be talking about now. We call it the field winding connections, because keep that in mind, all the time you will need voltage applied to the field winding, because we need a current moving through these windings to create the magnetic field. Seeing that this current or this current, we need a current moving through the coils, otherwise we will not create a magnetic field inside the machine. And the magnetic field is our medium of the energy conversion. We need magnetic field, so we need to apply voltage to it. Okay, so keep that in mind. It doesn't matter if it is a motor or a generator. Okay, we need to apply this. So whatever we have, so we need to apply electric voltage to the field winding to pass current in its coils to create the magnetic field needed, let me say, as a medium for energy conversion. Okay, whatever the machine type we're talking about. So if it is a generator or it is a motor, whatever it is, we have to apply voltage to the field winding. Okay, so in your mind, just imagine it like this. In a motor mode, if you have you need a motor, you apply voltage to the armature and you also to apply voltage to the field winding. So you have to apply voltage to both of the winding. Okay, if you're talking about a generator, you need to apply voltage just to the field winding to create the magnetic field, and then apply external rotation and the voltage will be induced in the armature. Okay, so in both the modes of operation, if it is a motor, if it is a generator, we need to apply voltage to the field winding. And that's how we will now talk about how to apply voltage to it. Okay, so you have three different ways to do this. The first one, we call it separately excited DC machine. Okay guys, what is this? Basically, from its name, it's separately excited. That means we use a separate voltage source for the field winding, and that means you use another source for the armature in case of a motor mode. Yeah, because we know if we have to operate the machine as a motor, we have to apply voltage to the armature because your input is electrical energy, so you have to apply voltage to the armature. But if you are just dealing with a separately excited machine, that means you need a separate voltage source for the field winding. So if it is a motor, you need two different DC sources. Okay, how to model this? remember, again, there is the armature circuit. That is the R armature, and that is the induced EMF inside the machine, and that is the V terminal. Okay, so that is V terminal, and that is the induced voltage inside the machine. Okay, with this positive negative, this will be positive negative, and you know this. Okay, and this is the armature equivalent circuit. Okay, how to model the field winding? It's in the same way like this, but it is just have the field winding resistance. And now, because you are having separately excited machine, you will have a separate source. So I'll be adding here a source. It is different from this V terminal source we have in here. This one we call it VF, the field voltage. It will be positive negative like this, and that means that will be IF, and this will be IA, I armature, and this IF, which is I field. Okay, remember guys, we are talking here about just when you just modeling the field circuit here, it is just a voltage source applied to a resistor. It's nothing more. It doesn't have this induced voltage inside because the field winding is not rotating. If you remember, the induced voltage equals K phi times omega, okay, times the speed. That's what I need. So it is related to a speed term. Because the rotor, which is the armature, is rotating, you have induced voltage like this. But if you're talking about the field winding, it does not rotate because the field winding is fixed on the stator. Okay, that is the iron steel core of a stator. And the stator does not rotate, does not go anywhere. So that is how you model both of them. That is the armature circuit on the right hand side, and that is the field circuit on the left hand side. And because you're talking about separately excited machine, you have two different sources like you see here. Okay, what are the advantages of this? This everything has pros and cons, yeah. So the pros of this guy is just we have full control over the field current IF by controlling VF. So if you just try to control the amount of magnetic field you have inside the machine, it's easy. Just control the VF, the voltage applied to the external, because it's just different. It's a separate source for it. Okay, and by controlling this, you basically controlling the phi, the magnetic field on the machine. Yes, that is the pros here. What about the cons? Yes, it's obvious using a separate DC source is expensive. Remember, we're not talking about a small toys machines where you're just having AA batteries or something. You're talking about the big machines. So you need a big source to get the electricity you want, and having two different sources, if you're talking about a motor, obviously, that means, so yeah, if you have just adding this voltage here, that means we're talking about motor mode, you know this, because if it's not a motor, if it's a generator, we're not adding a voltage to the armature, because basically the voltage is getting out of the machine. We get induced voltage because that's a generator. Okay, rather we just apply a source to it. Okay guys, so you know this. Let me have it for you. So if it is a motor, it will be just the field winding RF, and we have VF like this. And if it is a motor, you will have the armature circuit just like this. You have another voltage source here, that is the terminal of the machine, and that is our armature, that is E armature, and you have the current going inside the machine because that's a motor, and that is IF. So that is for a motor mode. For a generator mode, it will be the same field circuit, and that's why I'm saying we need voltage applied to the field circuit irrespective of the type of the machine, okay? And that is the armature circuit. That is EA, and now you have this terminal, and the current is just moving out of the machine because that's a generator. And rather than having a voltage source like this, you will be having a load, like a resistor or load. Okay, guys, because that's a generator, like this, okay? And yeah, there will be just voltage here, positive, negative V terminal, but that is the voltage across the load. It's not applied source to the machine. You know this, guys? So if you need just to model those, you'll have two equations. For the armature, V terminal will be equaling EA plus IA RA. That is for motor mode. So the plus goes for the motor mode, and the negative goes for the generator mode. Yeah, we know about this because, yeah. So in a generator mode, EA is higher than the terminal voltage. The induced voltage inside the machine is higher than the terminal voltage, while in the motor mode, the terminal voltage is higher than the internal voltage. We just talked about this at the very beginning of the lecture. So for a motor mode, V terminal equals EA plus IARA. Like this, V terminal is higher than EA, the induced voltage. For a generator mode, V terminal equals EA minus IARA. Like this, in the generator, you will have the induced voltage higher than the terminal voltage, and that makes sense because the internal voltage has to be higher than the terminal voltage for the current to move out of the generator to the terminals, go into the load. Okay. For the field winding, you just have the equation VF equals IF RF from Ohm's law. Okay, guys, what do we know like this? If it is a motor mode, we need two sources. One for the armature, which is V terminal, we call it like this, and one for the field, which is V field. But as a generator, we need just one source for the field winding, which is VF, and your machine will be the source which supplied electricity to the electrical load. We're talking about a generator. Okay, guys? So that's what I mean by separately excited machine. You have two different sources, one for the terminals of the armature and one for the field, if you're talking about a motor mode like this. Before I jump to the other types of connection, let me just emphasize one important thing here. What happened when we applied this V field applied to the field winding? Yeah? Basically, you have voltage applied to windings, so IF will pass through them. Yes? And this IF creates the magnetic field phi. So phi is directly proportional to IF. So if we try to draw IF versus the flux, you will be having like a linear relationship, just a line like this. Yes? Yes. This until a certain amount of current. The whole point, guys, if you have a piece of iron or steel, which we make our just coils of, or make our cores of, and we just strap the coil around it like this, and you have IF just moving through this. That's typically the case, yes? While you increase this amount of current, the field which being created from this will be start increasing, so you will have flux lines like this inside this core, iron or steel. So you keep increasing the field, and these lines will keep increasing. So you have more lines and more lines. But you will hit some point while this piece of iron or steel doesn't have any space for any more lines. That's what we call saturation. It doesn't have any more. And that means this relationship will not be linear anymore. It will be just going through like this. It will start saturating. So while if is just small enough, you will have a linear relationship. While you increase if, the flux will increase by the same ratio until you get higher field current enough, and then you are entering saturation region, and that means the increase in I field will not be translated to an equivalent increase in the flux because there is no space for added flux lines inside this machine. That's why for here that's linear relationship, here it's non-linear relationship. It depends on the amount of just current you are just passing and the size of the core of the iron or steel core you're using. Okay, that's a piece of information you should have in before in electromagnetic courses, but it's just worth mentioning here. Okay, guys? Nice. So that was the first connection, which is the separately excited. The second connection, is the shunt excited DC machine. From its name, shunt means parallel. Okay? And what does it mean? Is connecting field winding in parallel with armature winding. Okay, guys? So, like this, we just have it like this. Rather than having different source for each one of them to the same source, if you're talking about a motor. Exactly. So the whole point is just here. Remember your armature circuit, it will just like that. That's our armature, and that is the induced voltage inside the machine. That's your armature circuit. Yes? What you do basically is you just have your field winding connected between them at the same terminal like this. And now you have V terminal like this, plus minus V terminal. So now the field winding and the armature winding are connected in parallel at the same points, these points. And by using this, if it is a motor, you can just use one source applied to both of them. So you get one source and you will just supply electricity to both of the windings. And it just looks smart. So this current now is called I terminal, coming from just if it is a motor, so this is for a motor mode. That means we are applying DC source like this. And the current here will be I field, and the current moving through here will be I armature. Okay, guys? By the same idea, if you're talking about the generator mode, it is still the armature circuit like this, and here by connection is the R field. So that is the field winding, and here is EA for the armature. But now the current is moving out of the machine like this, so that is I armature. And this is the current is going to the terminal, going out of the machine. And rather than having a source outside here, you will be having a load like this. So it is R load. And this induced voltage coming out of the machine will supply voltage to both the load to move the current out of the machine to the load. At the same time, it will be just supplying current I field moving through RF. So the amount of voltage that's getting out of the machine will go to the load to supply to the electricity like a generator, but at the same time some of it will be used to just be applied to the field winding to create the current and creating the field. Okay, guys? So that's the whole point here. Now you have just the field winding and the armature winding and just connected together like this, parallel to each other. Okay? But like this, we use the flexibility that we had before, because when we have separately excited, so separately excited is more flexible in terms of control. So you can control the magnetic field, control of the magnetic field. Yes? Here, what to do to control the magnetic field? Before, in the separately excited, we just need to do nothing but to control this VF. If you play with VF, increase it or decrease it, you're increasing the IF, the current, or decrease it, and that increases or decreases the flux. But what to do here, to do this, we cannot play with the terminal voltage, because terminal voltage now is not just applied to the field winding, it applies to both of the machines, to the field winding and to the armature winding. Okay, so it's not just flexible, because if we don't need to change the voltage of the armature, but we need to change the voltage of the field, we cannot do this here, because both of them are connected in parallel to the same source. Yeah? So what to do? What we usually do here for shunt connection, it is just we add a variable resistor, a potentiometer, in series with the field winding. So this is our field, and that is our adjustable. And this guy is just a potentiometer. By controlling this adjustable resistor, this controls IF, and this controlling the flux phi. Okay, so rather than just having the field winding, we add an adjustable resistor in series with the field winding. Add our adjustable in series with field winding. Okay, that is how we can control the flux and the shunt connected circuit. Okay, so it is now easy. You just have the same idea again. If we're talking about a motor here, that is RF, and that is our adjustable. And that is our armature, and that is the induced EMF inside the machine. If we are talking about a motor mode here, the terminal of a motor mode here. Now, by just controlling this resistor, you will controlling I field without controlling I armature. Okay, so the I armature will be just not played with like this, but playing with this resistor will control this field current up and down while keeping I armature constant. Okay, so this is how we can control this. Okay, guys, so controlling our adjustable controls IF without changing the armature current. Okay, guys, and that's how we control the flux here in the shunt connected. Okay, so before jumping to the third connection, which we call the series connected winding, let me first introduce you to a very, very, very important thing. We will be just looking at all kinds of machines, or we call it the torque speed characteristics. Torque speed characteristics mean the equation that relates the torque and the speed of the machine. And why is this important? We'll be seeing now. Okay, the torque of the motor can be calculated like K phi I armature, if you remember. Okay, and the induced voltage inside the machine equals K phi omega m. Those are the equations we got before. And that's why, remember, when I tried to play with R adjusted to control IF without playing with I armature. Why we don't like to play I armature like this? Because I armature directly controls the torque of the machine. So we don't like to play with the armature current because it will change the torque of the machine. And this thing needs to be just adjusted to the load torque you're trying to drive, because you're talking about a motor here. So we make sure that our machine generates as much torque as the load requires, and not play with it just to adjust the flux inside the machine. Okay guys, that's why we like to add the R adjustable to the field winding to just control IF without controlling IA, because controlling IA would play with the torque directly. Okay, so if you go back to the same equation, we said this for a motor mode, the terminal voltage equals EA plus IARA, yes, from the equivalent circuit. You just substitute this, EA equals K phi omega m, plus IA will equal the torque divided by K phi, yeah, and that is multiplied by RA. If we just do the math from this equation, you will get this line into this equation. Omega m equals V terminal divided by K phi minus RA divided by K phi squared multiplied by torque. And that is what we call the torque speed characteristics, because that's an equation that's related to torque and the speed, omega m and the torque. Okay guys, that is the torque speed characteristics. Okay, and that equation is just for the separately excited or shunt connection. So this can be applied to both the separately excited machine and the shunt connected machine. When we go to the series connected machine, which is the third connection, we'll be rederiving the equation for it particularly. Okay, it can be done like the same idea here, but the series connection machine has just a unique characteristics. So for this equation like this, you can just draw it because that's characteristics. So you can just draw the torque versus omega m. And from this equation, if you try to do it, it will be just some sort of a linear relationship that is going down like this. Okay guys, what do we mean by this? We mean if load torque increased, the motor torque T motor will increase, and this will cause the speed omega m to decrease. This coming from this characteristics, it says like this: when the torque goes up, the speed goes down. And it just makes sense, because adding more load to the shaft, it acts like a brake, and the motor generates more torque only of the load attached to it requires more load. So if the load, the mechanical load attached to the motor, starts going up, the motor has to develop more torque to just supply the requirements of this load. So the motor will generate more torque, but this will come with the cost, and just the speed of the machine will start dropping down like this. Okay guys, that's coming from this equation if we just keep everything constant. But we don't have any control over these characteristics. We have control if we control the flux, because if you see, the flux here is a part of the equation. So if we keep the flux constant, the characteristic will look like this. But what if we try to control the flux? if you increase the flux from this equation, K phi is just in the denominator, so increasing it will bring this characteristics, whole of it, down. So increasing the flux up will bring the characteristics down. What I mean by this means for a certain amount of torque like that, you will have less speed. So if we control flux to go up, increasing, the speed will go down for the same torque. You know what I mean? That means that is a control of the speed. If you are trying to control the speed of the machine, you want the speed to be up to just a value you need. And we do this all the time with all kinds of machines. That what we call by drives, the control of the machines. It is just if you're talking about an elevator or something like that, you will need the ability to control the speed of the motor that's lifting up or down the elevator to make it more convenient for the passengers. You need the speed to be as steady as possible, or you need the speed to decrease when you just reaching the destination, otherwise it will just be suddenly braked, and we don't like do this. So we need to have a control over the speed. So you can do it like this. Control the flux to go up and your speed will go down. Or vice versa. If you control the flux to go down, the speed will go up for the same torque. So you're still applying the same amount of torque, that's the load required, but a different speed, the one you control. And that's the whole point of control, guys. That's the first hint of how to control the speed of a machine. If it's separately excited or shunt excited machine, we can control it by controlling the flux. Remember the adjustable resistance we added here to the field winding? So if we increase our adjustable value, the current will be decreased, and the current IF decreased, the flux will decrease, and the flux decreases, the speed will increase at the same amount of torque. So you're still supplying the torque the load wants, but at a higher speed that you determine yourself, because you want to make it more convenient for a certain application. And that's what we need by a control. So controlling the flux here, control the speed. Okay, guys? By controlling the flux, you can control the speed. So if the flux goes up, the speed goes down at the same torque. And vice versa. If the flux goes down, the speed goes up at the same torque. Okay, guys? But that is the whole point here. Imagine if phi equals 0. If you have no flux at all, if you do not apply any voltage to the field winding and you don't have flux. So while flux is very small, the speed will go very, very high. Because we said, if the flux goes down, the speed goes up. Goes very, very high, which reaches infinity. So that's a very, very important hint to carry. That is why a separately excited or shunt DC machines, or say DC motors, must not started at 0 flux. That means you make sure you attach your field winding to the source, the electric source, to build the flux before you apply the voltage to the armature of the machine to make it rotate as a motor. Because if you do this, the machine will start at the 0 flux, or at least a very, very small amount of flux, and this will make the machine to jump at a very, very high speed, and this may cause problems. It may break the rotor or may even have accidents. So keep that in mind even if you go to the lab. never try to start a separately excited or a shunt motor without applying a field winding to it. I'm talking here about basically a separately excited machine, because that is the one that is need a separate source. So never attach or never press on the button to start the terminal voltage of the armature before applying a field winding to the field, applying field voltage to the field winding first to build up some flux, because the flux is very small, the speed will be just very high, and we don't like to do this. Okay, guys? Okay, that's okay for now. Next time we'll be just keep on going with this for the third connection, which is the series connected machine. Thanks so much for joining.